So our first paper is titled "A Disposable Sensor for PM2.5 and the PM10 based on wireless magnetoelastic resonators." The authors are from University of Michigan and Arbor. However, they cannot make to the conference for this time, and therefore I have agreed to be their presenter for this paper and deliver the presentation. So let's get started. So first, the background. As many of you know, the exposure to the fine particulate matter, or PM, are well known to have close relationship with lung and heart diseases. With the increasing awareness of the air quality on people's health, there is a strong need for the development of small and no-cost PM sensors for regular citizens to monitor the PM2.5 and PM10 exposure. Most of the low-cost PM sensors in the market are based on the optical transduction, which has constraints on the detectable particle types and the sensing resolution. Frequent calibration is also critical to avoid influence of optics contamination and change of environment particle types. So more recent study explored using the piezoelectric-based micro-machine resonator as a replacement. The piezoelectric resonators did avoid the problems related to the optical transduction. However, they require electrical connection for signal feed-through, which brings out difficulty for long-term use and replacement. Additionally, the lifetime of the previously reported resonators is limited due to the restricted sensing area. In contrast, the magnetoelastic, or ME resonators, which are routinely used for disposable anti-theft tags, present an alternative that is both low cost and wireless in nature and is highly amenable to disposable usage. As we can see in the figure on the bottom right here, the ME devices vibrate at their resonant frequency in response to an applied oscillating magnetic field. The bottom right figure over here shows the DC magnetic field is applied to bias the sensor in order to get the optimized and linearized sensor response. The vibration of the ME resonators in turn launches the magnetic waves, which can be sensed externally by using an inductive coil. This coil, the top right figure here, actually shows an example of the magnetoelastic sensing system used for the smart tag application. So inspired by the wireless nature of the ME resonators, the authors has designed the disposable PM sensor shown as the figure here. The sensing unit consists of a disposable sensor chip with integrated two-stage aerosol impactor, two ME sensors, and the bias and magnets. PCB coils and the screws and washers for easy assembly will be shown more in details on the next slide. The two-stage impactor enables the particle separation based on their diameters. The larger particles will be collected in the impact stage number 1, formed by a 2.5 millimeter length ME resonator, and the PM 2.5 will escape from the first stage and get collected on the impactor stage number 2, formed by two tips of the 5 millimeter length ME resonator. The sensors are coated with particle absorption material to reduce the particle bouncing effect and biased with a set of the magnets to achieve the optimized performance. Two sets of planar spiral coils are integrated into the PCB coil for driving the ME sensors and picking up the signal. The PM concentration will be measured based on the resonant frequency shift caused by the accumulated weight on the sensor surface. The two-stage impactor was 3D printed with embedded flow channel and the housings for ME sensors and bias and magnets. The sensors were fabricated from micro-EDN. From these two schematic figure on the left here, we can see that how the disposable sensor chip was assembled, and then the figure on the right shows the assembled sensing unit after the particle test. So you will be able to see the particles that's accumulated on the surfaces. The two-stage impactor is designed and the aerodynamic model is evaluated with console metaphysics. This figure over here shows the velocity field in the designated flow rate. And then the bottom two figures show that most of the PMs with 10 micron diameters are collected on the first stage, and the PM with 2.5 micron diameter are collected on the second stage. The simulated particle collection efficiency is shown as a plot on this slide over here, where we can see that the stage 1 has over 45% collection efficiency for large particles, while the stage 2 has over 70% collection efficiency for the fine particles. The tested sensors were taken out and scanned under SEM to check the size of the accumulated particles on each sensor, and the SEM results proved that the larger particles were collected to the first stage and the most fine particles were collected to the second stage sensor. The sensors were then tested using the particle test setup showing in this diagram here. A high PM concentration environment has been created in the glass flask, and airflow was introduced to this gas flask to ensure the particle circulation. A TSI commercialized particle counter was used to identify the particle concentration in the glass flask. And then driven by the micropump with the mass flow controller, the flow rate was set as 0.6 liter per minute, and the measurements were conducted with the sensors every 5 minutes. For the measurement results, first we're going to look at the sensor sensitivity. The sensitivity is defined as the sensor resonant frequency shift per sampled particle concentration. The plot on the left shows the sensitivity evaluation for the stage 1 sensor. You can see that the y-axis is the measured resonance sensor frequency, and then the x-axis shows the unit sampled particle concentration. The slope of this curve on the plots indicates the sensor sensitivity. And for the stage 1 sensor, this is 0.056 hertz per unit sample particle concentration. And then for the stage 2 sensor, this is 0.117 hertz per unit sampled particle concentration. This stage 2 sensor has twice the sensitivity compared to the stage 1 sensor. This is because the particles are accumulated to the two sensor tips, which contribute to more effective mass to resonant frequency shift for the stage 2 sensor. Then we're going to look at the service lifetime of the sensors. As the equation over here shows, we're defining the service lifetime for each sensor as accumulated mass, that is M, at the signal to noise ratio of 10. And then this is divided by the annual sampled volume and then over the annual PM limit. These two plots show the sensor accumulated mass evaluation for stage 1 and stage 2 sensor. The x-axis is the accumulated mass, and the y-axis is the signal to noise ratio, or SNR. Then this left plot shows the accumulated mass when the SNR is approximately equal to 10, and that is given the number of 22.5 microgram for the stage 1 sensor. And then this right plot is for stage number 2, and when the SNR is approximately equal to 10, this accumulated mass is 95.4 microgram for this stage 2 sensor. Then if we assume that the test environment satisfies the AQI 50 standard, that is the air quality index 50 standard for the PM2.5, and then we also use the WHO standard for the PM10, then we can calculate the stage 1 sensor has a service lifetime of over 416 days, And the stage 2 sensor will have a service lifetime of over 441 days. The stage 1 sensor has a lower signal strength for its smaller form factor, but also because it has a greater vertical distance from the radar coil on the PCB at the bottom of the sensor. So the table on this slide compares the ME sensor to the typical optical sensors and the piezoelectric resonator sensors for measurement of the PM. Compared with the optical sensors, the ME sensor has direct particle weight readout, better system resolution, and a much reduced calibration and sensor chip cost. Compared with the piezoelectric resonators, the long service lifetime and the easy replacement feature made the ME sensor suitable for long-term daily use. The system resolution of the ME sensors can be adjusted with different operation modes to fit the different test conditions. Now, for the conclusion of this work, the authors has designed the first disposable wireless PM sensor based on the magnetoelastic resonators, fabricated and tested with poly-dispersed particles, which is basically the particles with a variety of the size ranges. They have achieved this fabrication and the successful test of this with these poly-dispersed particles. Then the test results indicate that the both of the sensors have a good resolution and lifetime. In the future, the authors will do calibration tests with a series of mono-dispersed particles. That's basically the particles with a single range size to validate the particle collection efficiency of the two-stage impactor and conduct field tests to further evaluate the sensor's performance. They will also design more types of PM sensors to fit the different leads, for example, the PM0.5 sensing, high resolution sensing, and long lifetime sensors for high pollution area. For the bigger picture, the authors envision that the great potential for employing the magnetoelastic sensing system as an environmental sensing platform. They will work towards this future and hope their work can protect people suffering from air pollution and build a more environmentally friendly society together. Thank you for your attention. Since the authors are not here, so there will unfortunately be no question answer. If you have questions, please feel free to contact the authors at the email address, which should also be included in the paper that has